Okay, so now we're going to look at graphing the logarithmic function. And hopefully you've looked at the investigation that we assigned a couple of days ago, right at the beginning of the unit. We looked about doing this investigation, but we're just going to sort of repeat it right now. So we're going to complete this table and go off and look at it. So now we're doing the logarithm of x base 2. So let's see what that means. Again, I'm going to skip the 0 for a moment and go straight to number 2 here. So let's put in 2. So that means it's going to be log base 2 with a 2. That means what exponent do I put on 2 to get 2? So obviously that's 1. Next one, log base 2, and it's 4 this time. What exponent do I put on 2 to get 4? That's 2. Okay, up here, log 1 base 2. So what exponent do I put on 2 to get 1? Well, that's a 0. Then we get into our fractions. So log 1/2 base 2 says what exponent do I put on 2 to get 1/2? Well, remember, if you put a negative exponent, you'll get the reciprocal. So in this case, it would be -1. What exponent do I put on log 1/4 base 2? That means what exponent do I put on 2 to get 1/4? Well, we'll need the negative to make it a reciprocal, and the 2 will square it, and we end up with -2. Now, if we remember and go back to the exponential function, you'll see that this is the just opposite of it. So if we go back to the first slide, we see we had numbers -2 and 1/4, -1 and 1/2. And then if we look at the slide we're on now, you see it's the inverse. So 1/4 and -2, 1/2 and -1. So the x and the y's have switched places. That's true for all of them. The only thing that's different is this one here. This, when it's 0, this would be log 0 base 2. That means what exponent do you put on 2 to get 0? Well, that's impossible. 2 to the 0 is 1. 2 to the 1 is 2. 2 to the 2 is 4. So none of the positives works. And if you put negatives in, you get fractions. So what exponent do you put on 2 to get 0? There isn't one. So at 0, it doesn't exist. So let's go off and sketch this. So I'm going to start at 1/4, which is right about here, and -2. So that goes about there. 1/2 and -1. 1 and 0. 2 and 1. And 4 and 2. And we sketch this as the logarithmic function. Now, by seeing the graph, it confirms our idea that the logarithmic function is the inverse of the exponential function. Remember, the inverse means the x's and y's switch. So you see all these x coordinates here, x and y coordinates, this one switches and the x and y comes down here. So instead of 0, 1, it becomes 1, 0, the x and y switch. How about this one right here? This is 2, 4 on the exponential. Well, you flip that, you get 4, 2. So all these points are inverses. 1, 2, 2, 1. The other thing that's an inverse is the asymptote. The original exponential function has a horizontal asymptote at y equals 0. Well, what if you do the inverse of that? Well, that results in a vertical asymptote at x equals 0. And then finally, if you look at this dashed line through the middle, if we remember back to inverses, another way of imagining it is taking the blue one and folding it over top of that crease to create the green one. All of this confirms that the logarithmic function is the inverse of the exponential. So I tried to demonstrate and prove it using the graph. I'm also going to prove it algebraically. So we're going to prove algebraically that the inverse of y equals 2 to the x is log x base 2. So we're going to go back and do the steps that we did in the first unit, where we have to find the inverse. Well, step 1 is to change it to y equals 2 to the x. Then we switch x and y. So the y becomes x, and the x becomes y. Now, the next step is to solve for y. That means we got to get y by itself. Well, the problem is it's up in the exponent. We can't get common bases, so we need to take the log of both sides. So log x equals log 2 to the y, log x. Now, of course, that y can come down. So it's y log 2. That gains us access to the y. And now I got to get y by itself. So I'm going to divide both sides by log 2. And I'll get log x over log 2. And if you recall, another way of writing that is log base 2 x equals y. That's our shortcut. Remember, if we were going this way to use our calculator, we would take the log of this number divided by the log of that number. So there it is, the log of this number divided by the log of that number. Well, normally we go, this way. This time I'm saying, hey, that is the same as this. Then that is right here. So this is just the algebraic proof that the logarithmic function is the inverse of the exponential. So that's all good information. Now, how do we sketch the log function? Well, here's an example of a sketch. This one's base 3. The ones we're going to do later are base 2. But you see the characteristics are still the same. This spot is going to be the same. It's going to be 1, 0. It's all the graphs are going to go through 1, 0, because that says what exponent do you put on any base to get a 1? Well, that's a 0. So we get 1, 0. The other thing that's common to all of these is you've got now, instead of a horizontal asymptote, you've got a vertical asymptote. The other thing that's good news is the logarithmic function behaves just like all the other functions. You can shift them left, right, up, and down. So this particular example says, hey, can you take the log function and move it 1 unit down and 2 units to the right? So I'm going to move it 1 unit down. Oops. I'm going to move it 1 unit down. So there it is, moved down 1 unit, and 2 units to the right. So 1, 2. And now we have our new graph. Let's just verify that we did that right. So there's the blue one, and yeah, it looks like we've moved the red one pretty well. Maybe just up a little bit. So what would the equation of this be? Well, it's the exact same thing as before. If this one has moved 1 unit down, that's outside the function, and we'd have a -1 someplace. 2 units to the right would be inside the function and opposite to what we think. So how would that look in this case? Well, y equals log base 3. Inside the function would be inside these brackets. So it's 2 units to the right, so it's going to be -2 inside the brackets, opposite to what we think. So that, of course, moves it 2 units to the right. And how do we move it down 1? Well, it's outside the function, so it's just going to have a -1 at the end. Just like in the other one where the horizontal asymptote moves, the vertical asymptote is going to move. So the vertical asymptote is going to move down 1 as well, but that's not going to, you're not going to notice that because this is infinite on both sides. But you are going to notice that it moves right 2. And I should actually have my graph over a little bit. So the vertical asymptote moves to x equals 2 because it's moved right 2. Just like we could reflect the other one, we're going to reflect this on the x-axis, except this is on the x-axis, so it's a reflection up and down. So reflections up and down mean that we're on the outside. Again, let's see that reflection happening. So there it is, reflected up and down. So there's going to be a negative someplace, and since it's up and down, we're going to reflect it, or we're going to put the negative on the outside. So it'd be y equals negative log base 2 x. So then we get to this stage where it's log x plus 3 base 2 minus 1. So I know that we could probably identify these pretty quickly. We see it's plus 3 and it's inside. So that means it moves left 3. And this part tells me it moves down 1. Again, I'm going to draw the original function as a reference. So it goes through 1, 0, and then here, and then here, and then here. And then here. Sketch that lightly. And that whole thing has to move left 3 and down 1. To help me, I'm going to move my asymptote. So there's my original asymptote. It's going to move left 3. So 1, 2, 3. That's going to be a good reference point. I think the other good reference point is going to be this spot here. It's going to move left 1, 2, 3, and down 1. So all the points are going to do that too. This one's going to move left 3, down 1. This one left 3, down 1. And I see then I've got this spot, and this spot. And it comes close to the asymptote, so I'm going to draw this. And if we check, we see that red graph is pretty much right on my green graph. Let's do another one. And you can try this if you want. So this one is going to move right 1 and up 2. I'll draw my original. I'm going to deal with my asymptote right away. There's my original asymptote. It moves to the right 1, so I'm going to put it here. Then I'll take my other steps and move it right 1 and up 2. So this one here, going to move right 1, up 2, 1, 2. And there's that spot. I think I'll erase those lines just so they don't get in the way. So right 2, up 1 puts it here. And the rest, I mean, you can move the other spots if you want. Right 2, up 1 would be, or sorry, right 1, up 2. Puts this one up here. This spot here, right 1, up 2 here. But I think now I can see that it's going to come close to this and draw that. Oh, looks like I made, this one went up a little too high. think I went up a little too much on that one. Okay. The last thing I might ask you to do is try and look at the graph and investigate what the actual equation is. So we're going to use this magnifying glass to go off and investigate this graph and see if we can't pull out some interesting information. So we look at it. We're going to take this magnifying glass. Oh, and we start to see there's a clue right there. So our vertical asymptote has moved to -3. So because the vertical asymptote moves to x equals -3, that means it must have moved in this direction because it used to be right here. So now it's moved over, so that means that this has moved left 3. So that's important. Are there any other clues? Oh, there's one. And I'm going to guess that that's that critical point. That critical point used to be at 0, 1. Sorry, 1, 0. Now you can see, so this spot here used to move, has moved to this spot here. Well, 1, moving left 1, left 2, left 3, we already knew about that. But now we can see that it's also moved up 2. So now, if I have that information, I know where the horizontal asymptote is, and I know where one of these key points is right here. I know that it moves left 3, up 2. How do I write that? Well, the original was y equals log x base 2. So this one has got to move left 3, so it's going to be log with a base 2. Left 3 means x plus 3. Opposite operation, or opposite to what you think. And then up 2 is going to have a plus 2 at the end. By the way, in this one, to help you, I'm going to tell you that you're looking for a logarithmic one. Okay? Because technically, this might have been an exponential curve that's been flipped, left, right, up, down, been flipped all over the place. But to help things out, I'm going to say it's an logarithmic. This one, same thing. I'm going to tell you that this is an exponential. Because you could imagine it as a logarithmic that's been flipped and up and down and all sort of stuff. I'm going to say it's exponential. So the first thing I'm going to notice is my exponential curve usually goes like this. And this blue one has been flipped. So I'm going to notice right away that it's flipped left, right. So that means within the function, I'm going to put a negative inside the function. So that part I can write right away. Remember, my base one is y equals 2 to the x. So if I'm going to put a negative, it'll be y equals 2 to the negative x. But more stuff might happen. So let's go off and check this. I'll just get rid of this black line. So what? So there's two things here. Okay, I've got a point right here at 0, -2, and I've got a horizontal asymptote. There's another big clue that the horizontal asymptote tells me that it's an exponential. Okay, horizontal asymptotes are in exponential, vertical asymptotes are in logarithmic. And the horizontal asymptote is down here. So that must mean that it's moved down 3. So I'm going to have a -3. So far that looks like a possible answer. The only thing left is to determine if it moves right or left. Well, let's remember the original exponential function goes like this. It goes through this point and then it goes off like that. So that's an important point, 0, 1. If I move it down 3, it would move down to this spot. Down 3 would end up at 0, -2. This then tells me I only moved it down 3. If I had moved it left or right, this point would have moved over here or over here. But it didn't, So this means that it's only down 3. There's no left or right, and therefore I know that this is my answer.